Okay, so good morning. I'm Lynn Parker. I'm chairing the session here that includes 6 of the papers that are being considered for Best Student Paper and Best Conference Paper as well. So thank you all for coming. I know the prior session was a little behind, so we'll go ahead and start right away. What we would like to do, all of these papers that are nominated for finalists for awards are being given certificates. All the authors are given certificates. And so if you're able to stick around as a speaker and as authors of these papers until the very end of this session, we would like to present you with the certificates for the paper and recognize your accomplishments for that. So please try to do that as the authors. And for those of you who are authors in successive papers in this session, if you could just come toward the front and be ready to go. So we're happy to introduce our first talk. Guy Rosman is going to be telling us about task-specific sensor planning for robotic assembly task.
Hi. So this work was done at CSL with all of these wonderful people. I'm now at TRI. We all know that robots are very effective in manufacturing. They allow us to be very productive and safe and cost efficient. However, an assembly line such as this is highly pre-programmed for a specific product, many degrees of freedom, all of them need to be taken into account. And we're looking for something more flexible in the form of fixtureless robotic assembly. In fixtureless robotic assembly, we are given a group of robots and a definition of a product. And given object parts, we would like to compose an object. We would like to instruct the robots how to place parts together, construct the object, arrange parts in space. And we need to plan for it. Maybe we need some sensors in order to reason about the locations of parts and robots and so forth. And this requires understanding of several concepts. This is a demonstration of such a system where you see the sensor and the manipulator robots going into place and manipulating parts of the object. In this work, we want to reason about the role of sensor planning. Sensor planning is given a set of possible sensor readings or positions or poses. We would like to pick the best one or the best sequence of choices. There are many tools to do that. Some of them are from geometry. Some of them include information theoretic concepts. And others are driven by efficient optimization goals. We say that we need to integrate better the role of sensor planning and assembly planning. We need to reason on how to deploy sensors. Sensor planning, by definition, needs to be specific to the task that we want to accomplish, and in this case, it is subtasks of the assembly plan. And sensor planning should be done within the assembly planning because we're basically modifying the environment as we go, and that affects our definition of effective sensor planning. Our approach is motivated by the following. Uncertainty and uncertainty reductions are a function of the state of the environment, and therefore they are a function of the plan. And different degrees of freedom are more or less important for different tasks, and we need to account for it. For example, if we look on the right at insertion of a key into a hole, perhaps the axial translation is not as important, but accuracy of rotation angle is critical. We therefore, in our approach, integrate the sensor pose selection into the high-level planner, and we plan for the sensor pose to maximize the predicted task success. The system which we've implemented our approach on includes a grass planner, motion planning, designing the motion plan, and a low-level controller for each of the plan segments. In our system, we assume that the robots are tracked by motion capture, so their state is well known. However, the parts that we assemble are not well known in their poses, and we need to estimate their position using a 3D sensor and ICP. If we know the initial position of parts before we do a low-level subtask such as insertion, we can complete the task successfully. If we have an error in the initial pose, we could have an unsuccessful insertion. Our approach is therefore the following. We sense before we do low-level manipulation subtasks such as insertion and placement. And we need to reason about two poses of the system, and by system I mean robots, parts, and sensors. We need to reason about the latent pose, which is the true pose of the system, and we need to reason about our posterior estimate of the pose, the sensed pose, and in our case it is sensed with a Kinect scanner. Now, we usually plan assuming the sensed pose, because that's what we have, and we execute sadly based on the latent pose. So if we knew these two poses, we could simulate and reason about the success of the task. And this is the approach we take. We sample from the latent pose based on an estimation of uncertainty. We then obtain samples from the posterior pose using the likelihood function, which in this case is highly efficient to compute on a GPU, and that's what we do in our estimator. And then, given these samples, we can compute a task success indicator, and we're going to marginalize over pairs of latent and posterior poses. Once we've done that, and this is a function of the sensor pose, we can attach the sensor pose to the rest of the plan and treat it as an overall plan for assembly. In this case, the way that we compute the indicator is the following. We start from the posterior pose. We build an open loop control. We simulate the execution of that controller starting from the latent pose. And while we do that, we reason about possible collisions and errors in the final state. If we had an accurate position of the parts, we could easily compute the insertion, for example, and that would probably be successful. If we have certain errors in the posterior pose, would lead to error in the execution that could cause the subtask to fail. We're looking here at open loop controllers, but we could have other controllers in that phase, which are reasoning about uncertainty or other additional constraints. What we have in our computation is basically a lower bound on the utility given a set of reasonable assumptions. The assumptions that we make, and these are detailed in the paper, are that the low-level controller for each segment is close enough in its result to the optimal controller in terms of the cost or utility. We also assume that the scene changes aside from the actuation of our robots are small enough so that the scene is static except for our actions, and that the success estimator, along with its reasoning about collisions and geometry, is accurate enough. Under these assumptions, we're computing a lower bound for the utility of the task, and this is what we wanted to achieve. Our planner is embedded within grasp planning that reasons about the possible grasp sequences to perform different assembly tasks with multiple robots, building on previous work with constraint satisfaction. We augment the grasp sequence with a motion plan and sensor pose. We reason about the task success probability, and then we select from all sampled tuples, we select the optimal plan, and then we execute. Our system includes 3 robots, 1 with a sensor and 2 with manipulator arms. As I said, the robot poses are estimated by a mockup system, and the parts are localized by Kinect. We're not assuming anything further about their localization. Our tasks that we performed include a peg-in-hole, Lego block insertion, and placement. And as we do that, we can also reason about this function of task success. In this row, we see the following. Suppose that we place a peg and a hole in the middle of the disk that you see in the 3 diagrams, and we allow the sensor to move around the assembled parts. we're guiding the sensor to look at the center of the assembled parts. And the question is, if we allowed only rotational translation, and in this case, our peg is a cylindrical peg with a 90 degrees in-cut in its side. If we allow only rotation arrow, and we look from different poses, different locations of the sensor, which places are more informative and allow us to reach better task success. The computed task success is what we see in the disk on the right. This is different from just looking at uncertainty reduction, which is the diagram in the middle disk. And as we do that, we also compute the number of effective particles, because a major concern with sampling methods is when you're trying to model rare events and your estimation becomes inaccurate. So what we see over here is that if we would look from the sides of the in-cut, we gain a big change in the resulting image. This means that the resulting uncertainty reduction would be large regarding the rotation, which means that we can localize well from the sides of the peg. However, if our initial uncertainty involved also translation uncertainty, it turns out that it's more efficient to place the sensor in front of the peg, giving us a good view of translational changes. And as you see on the right in row B, these are more informative. And here it's important to note that this is already different from uncertainty reduction, where translational uncertainty could dominate also in looking from the back of the peg, but it's not good enough for the task. Other examples are in the paper. It's important to note that in these diagrams, we ignore the placement of robots around the sensor, around the peg and hole or other objects, and this is just for the purpose of illustration. In the actual system, and this is our system in action, we actually reason before each insertion or other primitive, we reason about the position of the robots and the resulting occlusions, which are crucial when you have a more complicated assembly plan. To summarize, we perform task-specific sensor planning for robotic assembly. We embed it within the assembly plan, and we demonstrate the results with a team of robots. For more details, I'll be happy to answer questions or come visit me at the poster. Thank you.
Thank you very much. We have time for questions.
Yes?
Thank you for the very interesting talk. I have maybe one or two questions. First of all, when you plan the motion, do you also plan the kind of protocol or timing to double check the execution task and the recovery from when it is necessary?
So in this case, we're computing the probability of chance success, but we don't do later recovery in case of error. It's possible to do that, but it would be a different, basically at that point you would need to add a different change to the plan or add something else to account for it.
The last and second question is that maybe it is included in your talk, but I was not too clear how you take the advantage of multiple robotic systems in planning the motions or sensing.
Could you repeat?
So you have multiple robots, right? Mm-hmm. And you have more sensors than single robot. And where the advantage of multiple robot is being used in your algorithm?
In this case, we have a single sensor that's performing. We could have done the same approach for multiple sensors. Then we would need to reason about the combined reduction in uncertainty, basically taking into account both likelihood functions. And we could do that, but in this case, we had a single sensor.
Okay, thank you very much.
Any other quick questions? Okay, thank you very much. Appreciate it.